All right, go back to page 4 of the notes. So at the last part of that page, I mentioned to you that field strength is a vector. If you want to calculate the resulting electric field strength due to overlapping fields caused by several charges, you normally need to consider direction, because field strength is a vector in the first place, so you have to consider direction there. So how will you apply it? You look at the following page. So consider a case where you are interested to find the resulting electric force and the field strength at a point between two charged spheres. Okay. So in between the two charged spheres, you consider placing a positive test charge at a point along the line joining the two charged spheres. Okay. Now, each of the charged spheres, which is this charge and this charge here, they will tend to produce their own electric field and would overlap in the region between the charges, thus forming a new resultant field. What do I mean by that is, say for example, if you had a positive charge, isolated positive charge, you know that it will form an electric field like this. And then you have another charge right over here, again with its own electric field that looks like this. So these two charges were considered to be isolated because they're so far apart from each other, they don't influence each other. But what if you were to bring them close to each other? The left charge goes towards the right, and then the right charge goes towards the left. So if they are brought close to each other, eventually it will come to a case where they're so close to each other that the fields are actually overlapping now. Okay, so these two positive charges are brought so close to each other that the fields are going to overlap. So this one having its own charge like this, having its own field like this, and then this charge also having its own field like this, you can see that they tend to overlap at this region here, right? So this is the region where they overlap. At this region where they overlap, your fields will combine together and produce a new resultant field. Okay, so you're interested to find out in this region here, what is the resulting force, what is the resulting field strength at a point there. Okay, so at any point inside that region, the resulting electric force and field strength is actually due to the combined effects of the two individual spheres. All right, so how do you find out that resulting field strength or force? Is by considering that the force and field strengths are vector, you consider the directions accordingly during your calculation, whereby you assign a negative sign to vectors acting opposite to some assumed positive direction or to an assumed sign convention. Okay, so say in your first diagram here, you have examples for like charges, meaning to say it's either positive positive or negative negative. So I have a positive QA charge and I have a positive QB charge. So in the region between those two charges, there's one particular line that you are interested, this green line here. So at a point along this green line, you want to find out the resulting electric field strength, resulting electric force for a charge placed there. Okay, so say for example, you are interested to find out the resulting electric force for a charge that you place here. Say the charge that you place is a positive test charge, Q, positive Q. You place it here. In order to find out the resulting electric force here, you have to consider the individual effects of sphere A and sphere B. You have to consider the effects on the charge due to sphere A alone, and then you have to consider the effects on the test charge due to sphere B alone. Once you consider them individually, you add them up, okay? So how do you go about doing that? If you consider the effects on the positive test charge due to A alone, what do you suppose is the electric force acting on the positive test charge due to sphere A? because they are both positive, obviously the force acting on the positive test charge will be towards the right. Okay. Then you move your attention to the effects due to sphere B on the positive test charge. If now you consider the effect on the positive test charge due to sphere B, because again they are positive positive, the force acting on the positive test charge due to B will be towards the left. Okay. So this one will be the respective electric force due to each sphere on the positive test charge. FA towards the right, so FA towards the right, FB towards the left. So in your case here, if you then want to find out the resulting electric force there, we call this FP, is actually going to be FA plus with negative FB. Here you're assuming that going towards the right is positive. Okay, so once you consider that your resulting electric force is actually FA plus FB, you can now further expand your equation. Because you remember FE is written as this, isn't it? Let me just write it out at the right hand side here. FE is 1 over 4 pi epsilon naught QQ over R squared, right? So the QQ is actually the two charges involved, and then the R here does not refer to radius. Sometimes students have a tendency to mistake that. This is not referring to the radius. It's actually referring to the separation of the charges, separation between the charges. So now if I'm talking about what is FA, it will be 1 over 4 pi epsilon naught QAQ over RA squared. So the two charges for FA were this one, were these two. This one is positive QA, this is positive Q. The other one is QAQ. And then the separation is actually this RA here. The distance between the two charges, this is the RA. Okay. If you're talking about FB, FB would be 1 over 4 pi epsilon naught QB over Q times R divided by RB squared. So this one will be this one. The two charges is QB and Q. The separation is RB here. Okay. So this is the full equation that you would use if you want to calculate out the resulting electric force, resulting electric field strength, and whatnot. Okay. You can repeat this for field strength also. It's the same concept. So say for example, you again place your positive test charge here, and you want to find out the resulting electric field strength here, you are again to consider the individual effects due to each sphere before you combine them together. So I have to consider the effect due to sphere A. If I'm talking about effect due to sphere A, I put a positive test charge here. What is the direction of the electric field strength on the test charge due to A alone? Remember one of the things I mentioned to you, the direction of your electric field, your field direction tends to follow your direction of force acting on a positive test charge, and then subsequently your field strength also follows your field direction. I wrote it somewhere here under page 4. Okay, field strength direction is always in the same direction as the field electric field. So if originally you already determine what's the direction of force on a positive test charge is acting towards the right, the direction of your electric field strength on a positive test charge would obviously be towards the right also. It will be in the same direction. Okay, so your EA here is towards the right. Then you consider the electric field strength due to B. So because the direction of your electric force acting on a positive test charge here is towards the left, obviously your field strength due to B will also be in the same direction. So it will be towards the left too. So same thing, if you now want to find out the resulting electric field strength at that point, all you just need to do is you add them up. in your case, if you add them up, it will actually be EA plus with negative EB, because EB now is acting in the opposite direction. Okay, there's a negative to consider. So if you expand it out, you get 1 over 4 pi epsilon naught QA over RA square minus 1 over 4 pi epsilon naught QB over RB square. In your case, E, you do not need to consider the test charge. You only need to consider the charge that is producing the field. That's why here you don't see the small q. It's only the charge that is producing the field itself. Okay, so you expand it. This is your equation that you expect to see. All right. Okay, so there are some things there also, but this one I will probably skip it until I go to the relevant question. You go on to the next page. This one is another different example. The one that I just went through with you is for like charges, meaning to say the charges have the same sign. But what if you have a case where they do not have the same sign? They are unlike charges, meaning to say one of them is positive, one of them is negative like this. So you are going to do the same analysis the same way. All right, if you are interested in a point P along a line joining the two spheres, you need to consider again the individual effects due to each sphere before combining them together. But in your case, for unlike charges, it's somewhat easier because you see, if you consider the individual effects, you consider the effect due to A first. FA would obviously be towards the right. EA will also be obviously to the right too. And then you consider the effects due to B on the positive test charge, because this is now positive, negative, the nature of the force is attractive. The force acting on the positive test charge will be towards the right. The electric field strength due to B will also be towards the right. Okay, so now here you will notice that the directions are always going to be the same. There's no negative sign to consider here because none of them are acting in the opposite direction. If you want to find out what is FP, it will just be FA plus FB giving you this. If you want to find out what is EP, it will just be EA plus EB giving you this. Okay, that is how you are going to get the equation representing the region between the two fields. Okay. And then another thing I should probably kind of mention to you a little. If you go to the previous page, you're supposed to know a little on how would the graph of your field strength electric force look like when it's plotted against distance. So for like charges, it's normally like this. Okay. There is one particular point of there are some points to note from here. Usually, if you look at this particular diagram again, because your FA and FB, EA and EB are acting in opposite directions, there will come a point where your F net is 0, your E net is 0, because they are both opposing each other. At some point, if you go and shift your point P towards the left a little or towards the right a little, you will come to a point where they're equal and opposite, so that the net force, net electric field strength is 0. Okay, that one is represented by this point here. Okay, but if you were to then move a bit towards the left or a bit towards the right, you will get a net value, but they can be in opposite directions, represented by the positive and negative sign here. So what do I mean by that is this. You consider this. If you have moved more a bit towards the left, here what we'll say is that if you move a bit more towards the left, your RA would start to drop, your FA will start to increase. Your RB on the other hand will start to increase, but your FB will start to drop. Okay, because you see your RA and RB is defined as this. It's the separation between your main charge and the test charge. If you have moved a bit towards the right, if you have moved towards the left, this is what you expect to see. Okay, so that your FA starts to increase, your FB starts to decrease. When that happens, what you would tend to say is that your FA will be more than your FB. Okay, so if you move towards the left hand side here, like this, the thing that you will say is FA more than FB, your net force is actually going to be towards the left hand side because FA is more than FB here. At this point here, FA was equals to FB. That's why your Fnet is 0. All right. Now, if you move to the other opposite direction, going towards the right, your RA would now increase, leading you to have a decreasing FB, and then your decreasing FA, my mistake. Your RA increase, your FA will decrease, and then your RB decrease, your FB will increase. So from there, what you get is your FB is now more than FA. It's the other way around. So right at this point here, FB more than your FA, your Fnet will actually be towards the right. Okay, that's the reason why you're seeing this graph being like this. This portion here represents this region, and then this portion here represents this. Okay, that's why you will see the more you go towards one side, the more the effects due to that one will be stronger. Okay, that's how you get this particular graph shape here. You can also repeat this for your field strength. It's basically the same concept. Okay, this one is for light charges. If you move on to the unlight charges, this one would be somewhat similar in terms of the understanding, but there will be no Fnet equals to 0 or Enet equals to 0 here. Because like you see for here, because both are always in the same direction, you will never get a case where Fnet is equals to 0 or Enet is equals to 0. Okay. So from here to here, also, you're going from the left to right, your, maybe I don't do this. Yeah, maybe it's better just write this. If you go from the left towards the right, your Fnet will always be continuously towards the right. Your Enet will always be continuously towards the right. Okay, there will never be a case where your net force or net field strength will suddenly change direction, because in the first place, you just do not have any of them acting in the opposite direction. So there's no negative. You will never ever reach a 0. You will never ever get a negative. So that's why this graph shape looks like this right now. You don't see it suddenly changing to negative. It will be continuously positive. And also, it will never ever reach 0. You see how this graph is drawn? It doesn't go to 0. Because you see, when you add a positive and a positive together, it will just become a positive value. It will never ever become 0. If you try to add two positive values, it's just impossible for you to get 0. So this graph here, you will never get a 0. Okay, it will just reach a minimum point. Okay, so just be mindful of this particular graph shape.